All right, we're talking about Algebra 2, Chapter 3, Section 4. It's been a while since I talked about Algebra 2, but we're in the graphs chapter. So, we're talking about graphs. So, let's look at this problem. Determine whether this function, the cube root of x, is even, odd, or neither. State whether the graph is symmetric with respect to the y-axis or symmetric to the origin. And then they want us to look at the intercepts and then graph it. Okay, cool. So, since they don't want us to look at the graph from the beginning, that tells us that they want us to use like algebraic ways to determine if it's even or odd. So remember how that works. We talked about that before. We're gonna find f of negative x. We're gonna just replace x with a negative. And if the negatives just cancel out to get us just the normal function again, that means it's an even function. And it has y-axis symmetry. But if we plug in negative x and we can just pull the negative out, so we just get the negative version of the original function, that means it's odd and it has x. No functions have x-axis symmetry. It's the weird one. It has origin symmetry. And if neither of those things happen, which is plenty of the time, then it's just neither even or odd. So we're just going to do that for here. So our function is the cube root of x. So maybe the cube gives you a hint, but we're going to find f of negative x. So the cube root of negative x. And this is just kind of really knowing, like, if you take the cube root of a negative number, what happens? Because, of course, if you take the square root of a negative number, you get a imaginary number, I. But if you take the cube root of negative 1, what happens? Well, that's just a real number, right? Because you can do that. A cube root is multiplied by itself 3 times, and negative 1 times negative 1 is positive 1, but then again times negative 1 is negative 1. So the cube root of negative 1 is just negative 1. And more thoroughly, the cube root of a negative x is just the negative version of the cube root of x. And so you do just kind of have to know or understand that, but that definitely fits the definition of odd. Because look at how right here, that's our f of x. And so we just got negative f of x. So that definitely means that this is an odd graph and that it has origin symmetry. And so remember what origin symmetry means is it's just kind of got that, I always just think it's got a feel to it, is that if you flip over half of it and then flip it back over on the x-axis, or over the y-axis, you flip it like twice over both axes, it'll land back in on itself. So, determine the intercepts, if any. So, how do you find a y-intercept? That's the easiest. You always just plug in 0 for x. So, if we find f of 0, well, the cube root of 0 is just 0, because 0 times 0 times 0 is 0. So, that's going to be our y-intercept at 0, 0. But that's also our x-intercept. And we can try to find an x-intercept by setting the y value equal to 0. But look at how we'll just similarly cube both sides and get that x equals 0 cubed, which is, of course, just 0. So that's our only intercept. That doesn't help us a whole lot with the graph. So we know that it has origin symmetry, and we know that it goes through the origin itself, which often happens when it has origin symmetry. So let's just go to Desmos and take a gander at that. So let's see. My favorite way to do cube roots is to use fractions as exponents. So if we do x to the 1/3, that's the cube root of x graph. If you don't believe me, just to prove it to you real quick, you can come in here to Desmos and do the cube root of x, but that's just so much harder. But see how it's the same thing. Purple's better, so we'll go with the purple. And yeah, that's our graph. You see how what we have? the 0, 0, the y-intercept, the x-intercept, and you see how it has origin symmetry. If we flip over the 1/2 and then flip over the other half, it'll land back in on itself. I'm trying to think about how to show that really quickly on Desmos. That's not super quick to be able to show, though. So I think we'll move on for now. Because I think we're doing a very similar thing for the next problem. So we're doing the exact same process. So we'll start by finding f of negative x. And you see here our f of x is the absolute value. So we'll do the absolute value of negative x. And then so what's going to happen when we do that? Well, we all know the absolute value makes things positive. So does that mean we can just get rid of that negative? And well, it does. If it was like a 1 minus x, then it would not be so simple. But since it's just a plain x, that does mean that that's just going to be equal to the absolute value of x. You see how, I mean, just some examples. Maybe you don't need convincing, but honestly, I need convincing. That's always going to be the same, no matter what number we end up being there. So, what did we just find? We just found that when we plugged in negative x and we did f of negative x, we got just f of x. So that was a definition of even. So that tells us the graph has y-axis symmetry. You flip it over the y-axis and it lands on itself. All right, and then determine the intercepts, if any. Well, I think that's just going to be as simple as it was last time, because if we find f of 0, the absolute value of 0 is 0. And if we try to do 0 equals the absolute value of x, to try to find the x-intercepts by making the y value equal to 0, we would just get, if we try to solve it the typical ways, x equals positive 0, x equals negative 0, but both of those are the same thing. That's just 0. So, just like before, it's just going to go through the origin, 0, 0. And then so let's look at the graph. Go back to Desmos. We graph a couple of ways we can do it. Well, I guess, yeah, the quickest way is the symbols are right there. You can also do ABS, absolute. And there you go. That's the absolute value graph. And you run into that a lot. So that's like what we're going to get into the next section, is we're going to have a whole bunch of functions that you've just got to know the shapes of. And these are 2 of them that you've just got to know. I think there's like, 6 others? 7 others? But we'll get to there. Some of them you already know. Most of them you already know. But yeah, that's everything for that. I guess we did not fully appreciate everything we found, that there's our x and y intercept at 0, 0, and that if you folded this over the y-axis, it would definitely land back in on itself. And that means it has y-axis symmetry. All right, so now we got talking about piecewise functions. Piecewise functions freak people out sometimes, but they don't need to. So what this is one function. It's just defined in a whole bunch of different parts. And so the parts on the right side are telling you when, based on the x value, when to look at each part of the function. So if we just start with a, they ask us to find f of negative 2. So that means where x is negative 2. And so we look to the right and say, where does x equal negative 2? Or which of these conditions allows for x equals negative 2? And you see it's right there, because that's talking about how if x is between negative 3 and 1, you're going to go to that part of the function. So to get what it is, you're just plugging in negative 2 into this part of the function. So negative 2 times negative 2 plus 1. So f of negative 2 equals 5. And the other parts just don't even matter when that is the x value, when x equals negative 2. Now for the other one, let's do f of 2 next. When we do f of 2, so we're still plugging into the same function. We're still just finding f of 2. But we're looking at a different part of the function, because now you see 2 does not apply here. 2 is not between negative 3 and 1. but 2 is greater than 1. So that means when we do x equals 2, we're looking at this part of the function. We're plugging in x to that part of the function. So it's just 2 squared. So it's 4. And then I saved it for last, not because it's hardest, but because it's weirder, maybe a little bit, when x equals 1. What happens when x equals 1? So we're plugging in 1 to this function. And what do these conditions tell us over here? Well, this one is only when it's greater than 1. In this one, it has to be less than 1. And so we're looking at this one right here, because this one is when x is equal to 1. And then it just tells us when x is equal to 1, y is equal to 2. And so there we have it. F of 1 is just simply 2. So there we go. Determine the domain of f. So what is the domain? The domain is the x values you're allowed to plug into the function. So, well, what x values are we allowed to plug in? I guess that's what we got to look over here. We got to say, what x values do these allow us to plug in? Because at first it seemed like it could be anything. But look at this top one. This top one only goes down to -3. If we tried to plug in x equals -4 into this function, then we wouldn't have anywhere to plug it in, because that one only applies when x is between -3 and 1. If x is less than -3, this function's got nothing for it. So that's where the domain starts. You can see it can be equal to -3. So our domain will be from -3 up to, and where does it stop? So this one stops at 1, but this perfectly picks it back up again. We have something when x equals 1. And then this is just anytime it's greater than 1. It doesn't have a max like the other one had a minimum. So this domain just goes all the way up to infinity. There's no cap on what you can put in for x. Okay. Locate any x or any intercepts. Well, I always say, we know our rules to find x and y intercepts. You find them the same way every single time. So let's find the y-intercept first, which I also usually do because it's the easiest. I don't know why I erased all that. Well, I guess it's good. I can use the room now that I already did it. So locate the x-intercepts. So to find the y-intercept, so we just got to find f of 0, because the y-intercept is when x equals 0. And so we'll do it the same way we did before. We'll say if x equals 0, which part of this function are we looking at? Which piece of this piecewise function are we looking at? Well, when x is 0, this is the one that applies, because x is between -3 and 1. So you plug in 0 to the top one, -2 times 0 plus 1. So f of 0 is just 1. So that's the y-intercept. We have a y-intercept at x equals 0, y equals 1. Now the x-intercept is a bit more tedious, because any of these could potentially have x-intercepts, right? Because any of these could potentially output 0. So when we find the x-intercepts and we set the y value equal to 0, you really have to set all of these equal to 0. I mean, unless, of course, you're just going to think about it in your head. But as a process, all of these here could potentially output x-intercepts. And even once we get them, we're not going to be done. So let's solve all these equations. So we set all of these parts equal to 0. So here we get x equals 1/2. In the middle, we have nothing, which is clear. That's just when x equals 1, y equals 2. That's not going to produce an x-intercept. I just wanted to be thorough. And as you see, that equation is no solution. So that makes sense. And on the last one, we square root both sides, and we get x equals 0. So these are the potential x-intercepts. Because now, look, when we look at these functions, like for this x squared function, we're only looking at this x squared function. This x squared function, or I shouldn't even say function necessarily, this x squared part of the function only applies when x is greater than 1. So it's true that if we plug in x equals 0 into that function, or into that part, we'll get an x-intercept, but we're never going to plug in x equals 0 into that part. we're only going to plug in into that part when x is bigger than 1. So we might have got this as an x-intercept, but that's not actually going to be an x-intercept because that's not actually part of the graph. So that's the thing. You've got to check that once you find these. This one is between -3 and 1. And so you've got to go to the right part. So we went to x is greater than 1 when we looked at the x squared function. But now we're looking at the -2x plus 1. So we got to look to that part. Because when x equals 1/2, we will plug into that part. And we will end up getting y equals 0. So that will be an x-intercept. So now let's graph it. I feel like they want us to do it by hand, so let's do it by hand just for them. And then maybe we'll look at and talk about how we can do that on Desmos too. Because a lot of people don't know how to do piecewise functions on Desmos. I had to look it up for a long time before I finally remembered how to do it. So let's just start from the top. So we've got the line -2x plus 1. So, never sure what the best way to present this is. But let's start by graphing the line. So, you got to know how to graph a line. You got your y-intercept. You got your slope of -2. So, we start at the y-intercept. We go down 2 and over 1, down 2 over 1. And you see you just have your normal line, like you're used to. But the deal with these is we don't want that line everywhere, right? We only want that line from -3 to 1. So we could picture this now. We're going to come in and we're going to erase this graph everywhere besides that. So we're going to erase this whole end up until 1 because that's where we stop using that equation for this function. And then we also see that it doesn't even apply at 1 either. So we need to have an open dot there to show that. This one, it does apply at -3. So on the other end, we might as well put a closed dot to make sure people see that. But then what? So that's that part of the function. So we have it graphed from x equals -3 to x equals 1. And then we have our next part. It just tells us that when x equals 1, y equals 2. We can just do that, right? So we just go to x equals 1, y equals 2. That's just a point right there. And then the next part is where it gets a little trickier. So let me show you a couple different ways we can think about this. So it's x squared, right? So we all know the graph of x squared. But a lot of people get confused and try to start it here. So maybe they do it something like this. But that's not what this is saying. That graph you're looking at right now is not an x squared graph. The graph we want on our graph needs to be an x squared graph. So one way to think about this is if you start with that graph. So if we have this as our parabola, I don't know why it stops popping recently. There we go. So that's our parabola. But then if we think we don't want that entire parabola, right? We still want the graph of that to be the same. We just don't want the whole thing. We only want it when x is greater than 1. So what we have to do then, I guess that's hard to do with that there, but we have to erase this graph. This graph just starts there at -1. It does keep going, so we can put an arrow. But that's what this is looking like. So it's really important to see that it doesn't look like a parabola because it's only one little part. It's only the part of the parabola that goes straight up. So it still is a parabola, even though it doesn't look like it. You're not just shifting the entire parabola over. It's still just x squared. It's still right there in the middle. It's just one little part of it that you want. And so I was going to say is the other way to think about graphing this is, and this works well with lines too. The first line we did was pretty easy because its y-intercept was right there for us. We could just use the y-intercept. But if we didn't, and with this, a good way to do it is to think about just where it starts. So we know we start looking at this graph when x equals 1. So we can just figure out what does this graph equal when x equals 1. Well, when x equals 1, this graph is equal to 1. So that tells us right there that that's where it's going to start. And then from there, you can either just know the shape of the graph, or you could plug in the next value if you want. Like if you plug in 2, you'll get 4. So that's like here. And then from there, that shows you what the rest of the graph is going to do. So different techniques you can kind of come up with on your own. I think that's kind of fun. But the general what piecewise functions are, that's important to understand. That you have these 3 different pieces, and you're not looking at the whole function. You're just looking at the one part of the function. So let's go to Desmos and let's see how that's going to look. Let's keep it side by side so I have the functions. So we have the line negative 2x plus 3. So how you can do this on Desmos, there's a couple of ways you can do it, but one of the ways, the simple way, is to just you write the equation, and then you do the curly brackets, and then you write the inequality. So we say negative 3 is less than or equal to x, which is less than or equal to 1. And then it closes the curly bracket, and you see that's the segment of the line that we have. That's our purple segment there. As it's telling it we only want that graph in between those x values. You see there x equals 1, and here x equals 3. And then the next thing we just have is a point, 1, 2. And then the next thing we have is the parabola. So that's our whole parabola, like we graphed at the start. And then, I typed in this wrong. I was worried. That's 2x plus 1. So this is like our whole parabola like we had at the start. But then we don't want the whole parabola. We only want the parabola when x is greater than 1. And so you see that's like the branch that we have. So it's just the part of the whole parabola. You see there's your whole parabola, but they just want that green part of it there, not the whole thing. And so that's what piecewise functions are. Very important in the real world because things are not always consistent. So a lot of times if you're doing stuff like in real physics, you might have to use piecewise functions. Or if like something hits the ground, it bounces, its function's going to change. The absolute value function is a piecewise function, if you think about it. It's like the absolute value. Oh my gosh, I was going to write absolute value in H. The absolute value of x is like the piecewise function when x is negative, when x is less than 0. It's going to output negative x. So see how it's like if x is negative 2, it's going to output negative 2. It's going to output positive 2. But if x is greater than 0, it's just going to output a plain x. And then you got to put an equal sign on one of these. Doesn't matter. Just so 0 works. So then you see if x is positive, if x is 5, you're just going to output 5, which is what you want the absolute value to do. So even if you've never directly worked with a piecewise function, if you've worked with absolute value before, you have worked with a piecewise function. Ooh, maybe here we're doing a problem like that. So in the summer of 2009, Duke Energy supplied electricity to residents of Maine for a monthly customer charge of $4.50 plus 4.2345 cents per kilowatt hour for the first 1,000 kilowatt hours supplied in the month, and 5.3622 per kilowatt hour for all usage over 1,000 kilowatt hours in the month. What is the charge for using 300 kilowatt hours, 1,500 kilowatt hours? Was the monthly charge for X? So make an equation for it. All right, cool. So let's go step by step. Let's not just make the equation right at the beginning, as much as I would like to. Let's do the first problem. So what is the charge for using 300 kilowatt hours per month? So what do they tell us? Well, so the whole point of this problem, right, is they have a different charge for the first 1,000 kilowatt hours than they do for the rest of them. So if they're only using 300 kilowatt hours, we're going to be working with the first equation. So what does that mean? They charge They charge 450, so they're going to be charged 450 plus $450. Oh, well, we're gonna whip out a calculator for this anyway, right? So 450, 450 plus that's cents. So 0.042345 cents. Or what? No, we're multiplying that. We're multiplying that by 300 because that's what it is per kilowatt hour, and we're using 300 kilowatt hours. So then whatever that is, that's how much it's going to cost for 300 kilowatt hours. 300 times 0.042345 plus 4.5. So 17, I guess that's equals 17.2035. Okay. And then what's the next one? Because the next one we have to do a little more work, right? Because here they're breaking over that initial 1,000. So we have to think about this in two parts. Because see how they say it's not just if you use over the 1,000 they're going to charge you this amount. It's if just for the 1,000 you go over. It's just like taxes. That's like when people say if like you lose money when you make more because of taxes. It's not necessarily true. You could do it from other things, like other government benefits, but not necessarily taxes. So we have to account for that here too. So for the first 1,000 kilowatt hours, they're still doing the same rate. So to do this equation, to do this math, we're going to do the initial charge, 450, plus the same price for the first 1,000 that they use. But then we have to add on the rest of them. So what's the rest of them? Because it's not the whole 1,500. Like we said, we already paid for 1,000 of them. So there's only 500 of them that we have left to pay for. So then we're going to do this new price, 5.3622 cents times 500 kilowatt hours. And that's going to get us how much it would cost for that. And we're going to have to think kind of hard maybe when we write our equation. Because when we write our equation, we're going to have to account for that. And that's where the piecewise function is going to come in. That we're going to be using one equation if it's less than 1,000, because it's the simple one. But then when it's more than 1,000, it's going to be a little more complicated. So we have 450 plus 4 cents times 1,000 plus 5 cents times 500. So 73, 656. Yeah, there we go. So now for the more fun part of this question is actually writing the equation. So C is the monthly charge. So they want us to write a C of X and then a piecewise function. So let's think about the parts first. Because like we've already said, and like we saw when we calculated, there's only going to be two parts. There's going to be when X is less than 1,000. Guess we could say less than or equal to 1,000. Put it there. Put it there. When X is less than or equal to 1,000. And when X is greater than or equal, well, not equal, because we did it on the other one, when X is greater than 1,000. And so what are the two equations? We can really just look at what we did here. What did we do for the first one? We just did 450 plus that price times X. Because X was 300 in that case. Yeah, so that's simple enough. And then look at how in the other one we did something similar. At the end, we did the 5 cents times how many... Oh, no, though, because it wasn't times how many hours. That's right. So we might need some more room here. All right, so let's just start from the beginning. Because what are we going to do about this? Is that just going to be the same every time? It is if we're above 1,000, right? Because that's just the whole bit from the first part. And it's not just going to be automatically included. We have to include that in our equation. So let's see, first off, what is that number? Because we might as well combine it. We don't need to write all that out nastily. So 450 plus 0.042345. 0.042345. times 1,000. So you always got to make sure your answer makes sense. It does not make sense for that answer to be 4.54. 46.84 makes sense. So see what that means is that if you reach this tier of over 1,000, you're already paying this much for the first 1,000 based on the first program. And then we just have to add on whatever you're going to pay for the rest of it. But then it's not just as simple as multiplying by the x value here, right? Because we've already paid for the first 1,000. So how is that going to work out? I don't know why I'm not even writing on these lines. Can I redo this down here? So it's going to be 450 plus 0.042345x. See how nice my handwriting can be when I try? And then 46.845 plus what? That price per cent, 0.053622. But then not times x, right? Because we already paid for the first 1,000. So we're just going to multiply by x minus that first 1,000. And that's going to be our equation, our function. It's not a very good C. Our function to get our monthly cost. If x is less than 1,000, you can use the top equation. If x is greater than or equal to 1,000, you can use the bottom equation. And so, yeah, it is nice to notice that it doesn't matter where you put the equal sign. Because see how if x equals 1,000 and you do plug it into the last part, you would just get 1,000 minus 1,000 here, and that would just get it to cancel out anyway. So if you know it's continuous, which it should be in this situation, you can just put that equal sign anywhere. And that's this section. I don't really know what this section exactly was trying to get out of us. They showed us some piecewise functions. That's very important. I think that's like the only time in the whole book a piecewise function comes up. And little even or odd function review. So let's say maybe we did talk about absolute value here. So maybe they're trying to get us to think about, is that a piecewise function? Which we did talk about. We said it was. This isn't a piecewise function in really any shape or form. So I'm not sure what they're going about there. But that was good. Next is transformations. That'll be a big one.